Hi, distance friends. Let's do some practice problems via Edpuzzle. Should be good. So you ended the class with me on Monday with one of these types of problems, standard molar entropy for the following using the data table. So I attached a data table to this. You also have something called Appendix C in your textbook, which you may or may not care about. You can look any of these up online, and if you need them for the exam, they will be given to you. Of course, I closed my book, but Appendix C is great. It has all of these lovely thermodynamic quantities for selected substances at 298.15 K. Really nice. So you can see they give us enthalpy, free energy, entropy. Okay, and just check the units on those. Make sure you know what's going on. So in this type of problem, standard molar entropy. So this is going to be, and then we need to say whether it's increasing or decreasing. Okay. So remember, when we calculate these standards, the change in entropy is going to be equal to the sum of the number of moles of the products minus the sum of the number of moles of the reactants. So their entropy, right? Their entropy, their standard entropy. So this is pretty nice. We just have to deal with one on each side. So delta S is going to be equal to products. We have 2. And so then let's look up the entropy of NO2. So in my book, and let's just double check, this is as a gas. You better be checking for as a gas. In the book here, it says that the standard molar entropy for 1 mole of NO2 is 240.45 joules per mole K. All right, and then we are going to subtract all of our reactants, of which we only have 1, and we only have 1 mole of it. So we got to find N2O4, N2, and all of these are usually listed alphabetically. So all the N's are together. So here we go. N2O4's entropy is 304.3 joules per mole. Okay. All right. Not too shabby. So then just snag out your calculator and get an answer. Okay, so I got positive value. I got 176.6, and that's going to be joule per Kelvin. Okay. And so let's think, is entropy increasing or decreasing? Well, we got a positive value, so entropy is increasing. Okay. We can do the same thing, okay? So we also learned this for calculating the enthalpy of a reaction, right? We use the standard enthalpies, enthalpy of formation, to get delta H. We can do the same thing for delta S. We can also do the same thing for delta G. What a nice relationship. So we have the same thing going on here, okay? So we can use the enthalpy of formation data to calculate the standard free energy change for a reaction. So let's try it. P4 and Cl2 yields 4 PCl3 at 298 K. So get this set up. Pause, and then we'll come back. Okay, so I have mine set up. I know that delta G is going to end up, delta G of our reaction is going to be ending up 4 multiplied by the entropy of our PCl3, and then minus 6 times the entropy of our Cl2, and minus 1 mole of our entropy of P4. So let's just look up these numbers. So I'm getting that the entropy for PCl3 is negative 269.6. And that is in, just check your units, kilojoules per mole. Okay, and then we're going to subtract our amount of entropy from Cl2 free energy. Now, this is an interesting one. What do you think that's going to be when we look at Appendix C for Cl2? All right, that free energy is going to be 0. Okay, so let's remember that the enthalpy and that free energy is going to be 0 when it's in its natural state. Okay, and then let's just figure out what it is for P4. So the entropy for P4 is going to be 24.4 kilojoules per mole. That's going to be multiplied by 1 mole. Okay, so when we do this math, go ahead and get an answer. Tell me what you got. Okay, I got negative 1102.8 kilojoules, because the moles cancel, is equal to delta G. Okay, so delta G for the reverse reaction. So we should get the exact opposite, right? When we reverse that. Okay. Sounds good. So what does this negative tell us too? Right? It means that this direction is spontaneous, right? Okay, good. Okay, so let's go through this. Where's the enthalpy term and where's the entropy term? So tell me which part is so we're just looking here. What part is the enthalpy term? Right there. And then this with the temperature is our entropy term. Okay, so when is delta G always positive? Okay, so delta G is always positive. So let's just think about this. If it's always positive, well, it means that when we subtract a negative, that has to be a positive, right? So when entropy term is negative, right? Because then we're adding a positive that can only make it positive, and that would mean that enthalpy is positive. Okay, means that delta G is going to always be positive no matter what. Okay, hope that's okay. What does this correspond to? Well, it corresponds to being non-spontaneous if delta G is greater than 0. Okay, when is delta G always negative? What is it going to take? Well, it's going to take enthalpy being less than 0. Enthalpy has to be negative, right? And then our entropy has to be positive so that we're subtracting a positive number. Okay, so that will make it always negative. That means it is spontaneous in that direction. Okay. So our units, what are our units of delta H? Our units of T, and our units of delta G, and our units of delta S. Take a second and write those out. Okay, so delta G, kilojoules per mole. Delta H, kilojoules per mole. Okay. Now, temperature should always be in Kelvin. And then typically delta S is joules per mole K. Why am I calling your attention to this? Usually we're good with the K. It's that joules right here instead of kilojoules that gets people all the time, and they will ask a question checking to make sure that you convert that. So be really good about your kilo to base unit conversions. Good. Okay, let's keep going. Calculate the standard free energy change for the formation of NO from N to an O2 at 298 K. Given that delta H is equal to 180.7 kilojoules, delta S is 24.7 joules per K. Is the reaction spontaneous under these conditions? Okay, they're giving us values. That means that we should definitely be using this equation. They're giving us those numbers, and we should think about this in this way. So N2 plus O2 yields 2NO. Okay, so delta H, they gave it to us. It's 180.7 kilojoules, okay? And it's already been put in terms of per mole, right? That's why the mole's gone in here because it's already been calculated for these. Okay, minus temperature. So our temperature is 298 K. And then we've got this 24.7 joules per K. So 24.7 joules per K. So let's do the conversion right here really fast. So we have 1,000 joules for every 1 kilojoule. Okay, so that's going to be effectively divided by 1,000. So we're going to cancel out our joules. This will be kilojoules per K. Per K times K, that's going to cancel out. So we'll have kilojoules minus kilojoules. So this is going to stay 180.7 kilojoules and subtract this whole term, which is going to end up being 7.4 kilojoules. And our final answer is 173.3 kilojoules. Okay. Without looking up any data, predict whether delta G for this reaction is more negative or less negative than delta H. Okay, so we don't have to worry about delta H. We're just going to think about our minus T delta S. Okay, so how I like to think through these problems. Okay, so if we're taking negative 2,220 and we're subtracting this term, and we're wondering if delta G gets more negative or less negative. Well, for delta G to get more negative, S would have to be positive. And delta G gets more neg. Okay, more negative. So let's figure out, is entropy increasing or is entropy decreasing in this situation? So everything, here's what we have. Okay, this is interesting. We have gas, 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 liquid. So that automatically makes me think that because we're forming a liquid, that's going to have less entropy, right? And we're going from 6 moles to 7 moles, but 6 moles of gas to only 3 moles of gas. So I would say that this is decreasing in entropy. S is getting more negative, which actually makes this term more positive. So I would say that delta G is going to end up being less negative. It's going to gain some value from here. Okay, use the data to calculate it. Okay, so for this type of problem, we're going to use our enthalpy of free energy. Sorry, I just mean free energy, not enthalpy. So just our free energy values for this. So go ahead and look those up. Think about how we're going to do this. We're going to take products, subtract reactants. So 4 times the entropy of water in the liquid form. Make sure you look at the right one. 237.13 kilojoules per mole. Okay, and plus our 3 times the enthalpy of carbon dioxide, which is negative 394.4 kilojoules per mole. Okay. And then minus our C3H8, so that's 1. And the enthalpy, or the standard free energy, sorry, can't talk today. So we're doing all standard free energy numbers. So I'm looking at these, okay? I'm sorry, I'm mixing up my words. So we're looking at all delta G's for all of these. Okay, so the free energy for C3H8 is negative 23.47 kilojoules per mole. And we're going to add that to our 5 oxygens. And that's an element in its standard phase hanging out, so that's just 5 times 0. Okay, so just get a little number, subtract that. I got negative 2,108 kilojoules. Okay. For the Haber process, delta H equals negative 92.38 kilojoules. Delta S equals negative 198.3 joules per K. Assume that delta H and delta S do not change with temperature. Okay, predict the direction in which delta G for the reaction changes with increasing temperature. Ooh, okay. So what's going to happen? So let's just think about this. Delta G equals delta H minus T delta S. Okay. So we're going to say these don't change. Enthalpy is negative, okay? delta S is negative. Okay, delta S is negative, which means this is going to become, we're going to be adding this. We're going to make this more positive. And so as T gets bigger and bigger and bigger, delta G is going to go toward the positive direction. And delta G moving in the positive direction means that free energy, right, makes it, if it's positive, means it's less spontaneous. So we are going to be less likely to make the ammonia as the temperature increases. So let's do our calculations. So we're going to have delta G equals delta H, so negative 92.38 kilojoules minus 25 degrees. So we need to put that into Kelvin, 298 K. See how they're checking us? Okay, and then our entropy is negative 198.3 joules per K. There are 1,000 joules in every 1 kilojoule. Okay, so get that calculation. Get that done, and I got that it's negative 33.3 kilojoules. Now, delta G at 500 degrees C, we're assuming these don't change. So 500 is going to be 773 K multiplied by negative 198.3 joules per K. Same conversion. So when we calculate that, I got that delta G is 61 kilojoules. So at this temperature, we will make ammonia. This temperature, we will not make ammonia. We will make N2 and H2. Oh, coming back to equilibrium. Interesting. Okay. Oh my gosh, we're almost there. So, great problem right here. Number 4, this is our last one. You have made it. Good job. So, is the reaction exothermic or endothermic? And remember, that only has to do with delta H. What's the sign of delta H? It's negative. So, that means we are exo. Oh, what a nice problem. Okay, does the reaction lead to an increase or a decrease in the number of possible microstates of the system? Doesn't this just mean entropy? They're just trying to say it a different way. How do we know? So let's look at entropy. Entropy is decreasing, so we are going to decrease, and we know by the sign of S. Okay. Calculate delta G for the reaction at 298 K. What? We got this, right? So negative 35.4 minus 298 K multiplied by negative 85.5 joules per K. Convert 1,000 joules in every 1 kilojoule. I haven't done this one before, so let's check it. Let's do it together here. So I'm going to take negative 85.5, divide it by 1,000. Okay. We're going to multiply that by 298. Okay. 25.479. Okay, then I'm going to take our negative 35.4 and subtract our answer. And I got negative 9.921. Okay, and we really should be about negative 9.9, and that's going to be in kilojoules. Okay, so your reaction is spontaneous at 298 K under standard conditions. Yes, delta G is less than 0. Not factorial. I'm just excited. Okay, hope those problems helped you out. Let me know if you have any questions. Nice job, Hounds.